Society for Advancement of Electrochemical Science and Technology SAIST in association with CSIR Central Electrochemical Research Institute, Karaikudi, and Amrita Vishwa Vidyapeetham, Coimbatore. We feel very much privileged to have distinguished professionals and esteemed dignitaries, budding young researchers, scholars, and students with us today.
Today, we have with us our Honorable Chief Guest, Professor U. Kamakshi Mudali, Vice Chancellor, Homi Bhabha National Institute, HBM, NI, Mumbai. Respected Guest of Honor, Professor Sagar Mitra, Indian Institute of Technology, Bombay. Dr. K. Ramesha, Director, CSIR Sikri, Karaikudi, President, SAIST and Patron, NCE-24. Dr. Bipin Nair, Registrar, Amrita Vishwa Vidyapeetham. Dr. Sashangan Ramanathan, Dean Academics, Amrita Vishwa Vidyapeetham. Dr. B. Subramanian, Chief Scientist, CSIR Sikri, Secretary SAIST and Convener NCE-24, and Dr. A.K. Nandakumar, Associate Chair, Department of Physics, Amrita Vishwa Vidyapeetham, Co-Convener NCE-24. As a mark of tradition and to begin the two-day convention in an auspicious manner, we invite our dignitaries to light the divine lamp marking the positivity and divinity.
Now I request our respected dignitaries to kindly occupy the dais. Over the next 2 days, we'll be sharing knowledge, celebrating research, and connecting as a scientific community. To begin this day on an auspicious note, I kindly request you all to rise up for the invocation.
நீராடும் கடலொடுத்த நிலமடந்த கெளிலொழுகும் சீராரும் வதனமென திகழ் பரத கண்டமிதில் தெக்கணமும் அதிர் சிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை நுதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறமியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
We request everyone to rise up for the invocation, please.
ध्यायामो धवलावगुण्डनवतीं तेजोमयीं नैष्ठिकीं स्निग्धापाङ्गविलोकिनीं भगवतीं मन्दस्मितश्रीमुखीं वात्सल्यामृतवर्षिणीं सुमधुरं सङ्कीर्तनालापिनीं श्यामाङ्गीं मधुसिक्तसूक्तिम् अमृतानन्दात्मिकाम् ईश्वरीम्.
Thank you all. Now I request Dr. B. Subramanian, Secretary, says to welcome the dignitaries with a floral bouquet. To welcome our chief guest, Professor U. Kamakshi Mudali. To welcome Professor Sagar Mitra, guest of honor. To welcome Dr. K. Ramesha, Director, CSIR Sikri, President, SAIST. To welcome Dr. Bipin Nair, Registrar, Amrita Vishwa Vidyapeetham. To welcome Dr. Shashangan Ramanathan, Dean of Academics, Amrita Vishwa Vidyapeetham.
Thank you, sir. Now I invite Dr. B. Subramaniam, Secretary SAIS, to provide a formal welcome address.
Good morning and greetings from SAIST, Society for Advancement of Electrochemical Science and Technology, to everybody. Respected Chief Guest, Professor U. Kamakshi Mudali, Vice Chancellor, Homi Bhabha National Institute, Mumbai, and guest of honor, Professor Sagar Mitra, IIT Bombay, and our beloved director, Dr. K. Ramesha, Director of CECR Secretary and President of SAIST, and Patron NCE-24, and Dr. Bipin Nair, Registrar of Amrita Vishwa Vidyapeetham, and Dr. Sashangan Ramanathan, Dean of Amrita Vishwa Vidyapeetham, and the co-conveners of this NCE-24, Dr. A.K. Nandakumar and Dr. M. Mulaganathan. I could find, yeah. And all the invited speakers and faculty members of this institution, Amrita Vishwa Vidyapeetham, and scientists from SICRI, and we have this administrative officer and Vice President Dr. Madhyarasu, and campus director of Amrita Vishwa Vidyapeetham, Menon sir, and all other student participants, research scholars, exhibitors, sponsors. On behalf of SAIST, I welcome you all. Let me briefly tell about the SAIST. SAIST was founded in 14th November 1964. As you are all aware, SAIST, as part of its various scientific activities, periodically organizes national conventions and international conferences to provide a platform to discuss advances in the area of electrochemical science and technology. SAIST has organized so far 77 national seminars and workshops, 16 international conferences, 13 ISAIST and 3 ISUPs, and 23 National Convention of Electrochemists, and this is the 24th edition. On various aspects of electrochemistry, eminent scientists are invited to deliver lectures to interact with the participants. In addition to the above, the NCE hosts special lectures in memory of Professor K.S.G. Das and Professor S.K. Rangarajan and Professor S. Satyanarayana, who pioneered in the advancement of electrochemical science and technology in India. As you all know, electrochemistry is central to achieving a net zero society. While fuel cells and batteries are crucial for decarbonizing transport, electrolyzers offer a sustainable route to producing fuels and chemicals such as hydrogen and ammonia. So with this brief introduction, I welcome you all again. Our DG, CSIR Director General, Dr. N. Kalachali Madam, was very keen to attend this NCE-24, but due to some ministerial program, she could not make it possible. However, she has conveyed her best wishes for the success of this convention. I cordially welcome Professor U. Komashimali, Vice Chancellor of Homi Bhabha National Institute, Mumbai, who has accepted our invitation to be the chief guest and also to deliver the Professor K.S.G. Das Memorial Lecture. Thank you, Professor. I welcome Professor Sagar Mitra from Indian Institute of Technology, Bombay, for accepting our invitation to be the guest of honor for the inaugural function and to deliver Professor S.K. Rangarajan lecture. Welcome you, Professor. It is our director and patron NCE-24, Dr. K. Ramesha, who has been instrumental in organizing this event, and his constant support and guidance throughout the program has made this event possible. I welcome you, sir. It is our honor to have Dr. Bipin Nair, Registrar, and Dr. Sasangan Ramanathan, Dean of Amrita Vishwa Vidyapeetham, illustrious institution at Coimbatore, who are generous in supporting this NCE-24 by providing all the necessary arrangements. I welcome both of you, sirs. I welcome Dr. A.K. Nandakumar and Dr. M. Mulaganathan, Associate Professors and co-conveners of NCE-24 from Amrita Vishwa Vidyapeetham, Coimbatore, who have taken enormous efforts and spent valuable time in supporting us. I welcome you, sirs. It is my pleasure in welcoming all invited speakers, exhibitors, sponsors. There are nearly 25 sponsors for this NCE-24, including the government agencies like DST, ANRF, CSIR, and BRNS, and all other gold sponsors as you see here, SICRI, RSI, Class 1 Systems, Biologic, and other sponsors. Thank you all and welcome you all. Last but not least, I welcome all the research scholars and student participants for whom this NCE is being organized. And I assure you all that these days, 2 days will be very beneficial and definitely enrich you with a lot of knowledge and ideas. Thank you all.
Thank you, sir, for the warm welcome. I request Dr. Bipin Nair, Registrar, Amrita Vishwa Vidyapeetham, to provide initial remarks about NCE-24.
Namaskar. Good morning, everyone. Professor U. Kamashimudali, Vice Chancellor, Homi Bhabha National Institute, Mumbai. Professor Sagar Mitra, IIT Bombay. Dr. K. Ramesh, Director, Central Electrochemical Research Institute, Karaikudi. Invited dignitaries, delegates to this conference, friends. It's indeed a real pleasure and a distinct honor for all of us here at Amrita Vishwa Vidyapeetham to have this privilege to host the 24th National Convention of Electrochemistry here at our Coimbatore campus. We are, of course, all cognizant of the fact that the principles of electrochemistry are crucial for numerous modern technologies, from energy storage devices like batteries and fuel cells to industrial processes such as electroplating and metal refining. So in the light of this understanding, we can indeed envision that going forward, electrochemistry will play a significant role in sustainable energy, environmental protection, and advanced materials. It was also highly intriguing to me as a biotechnologist that electrochemistry is also beginning to have an impact where electrochemical methods are providing a better understanding of redox processes in the activity of drugs and medicinals. So we have also witnessed the tremendous potential of the applications of electrochemistry in our work here at Amrita in the development of sophisticated sensors for biomedical devices and diagnostics. So with our focus here at Amrita Vishwa Vidyapeetham being on what we call compassion-driven research, the opportunity to host this major event, NCE-24, in association with CSI Sikri Karaikudi, will certainly provide the right impetus for all of us attending this meeting to gain from the wide-ranging depth of cutting-edge research, discussion, and interactions with all the experts who are gracing this occasion over the next 2 days. So I wish this event resounding success and the best opportunity to create partnerships and move ahead swiftly to the heights of collaborative excellence, cutting-edge research, and productive partnerships. Thank you. Namaskar.
Thank you, sir. Today is the 24th convention of CIST in emphasizing the advancements in electrochemistry and related fields. At this juncture, it's our pleasure to welcome Dr. K. Ramesha, Director, CSIR Sikri Karaikudi, President CIST and Patron NCE-24 to deliver the presidential address.
Respected Professor Kamashimudali, Vice Chancellor Homi Bhabha National Institute, Mumbai, Professor Sagar Mitra, Indian Institute of Technology, Bombay, who are the chief guests and guests of honor of today's function, and the eminent host, Dr. B.P. Nair, Registrar, and Dr. Sasangan Ramanathan, Dean of Amrita Vishwa Vidyapeetham, and NCE coordinators, and CIST functionaries, and all speakers, distinguished speakers, and my dear students. Good morning and vanakkam, and all warm welcome to NCE-24. So on behalf of Sikri, Central Electrochemical Research Institute, and as a president of CIS, it's my pleasure welcoming you all for this NCE-24. Along with that, I also thank the management of this special place, Amrita Vishwa Vidyapeetham, to host this NCE-24 here, such in a serene and holy atmosphere. SAIST, like SICRI started in 1948. SAIST, that time KSG Das, who was the director, he founded SAIST 1964. And of course, 1964, you can imagine 6 decades ago, perhaps electrochemistry was done at some pockets, SICRI, Indian Institute of Science perhaps, BARC and IGCAR. So then the director thought to create one society like the SAIST, so which will work as like the society to spread the knowledge of electrochemistry, popularize the electrochemistry all through India and even abroad. And with that noble thought, he founded SAIST. And for the last 6 decades, SAIST has been doing this noble job of conducting the conferences, workshops, like national and international in alternate years. And last year we had international. National usually we will have in a place like colleges like this. So the idea is that so that we can attract the students community and we will be able to impart knowledge about electrochemistry, can teach electrochemistry. So that is the idea. So I think around in last 6 decades, SAIST has organized around 120 conferences, workshops, and national conventions like this, NCE-24. So with that noble idea, and also during the subsequent years, we also thought, let's have some memorial award lectures. That's 3 in sequence. One is for SKG Das and then Professor S.K. Rangarajan. These were the eminent director of SICRI. And Professor S. Satyanarayan has such a contribution, like, in the field of electrochemistry, particularly in batteries, like, being professor from Indian Institute of Science, Bangalore, and then, of course, ISRO work. So much contribution from these 3 great people. So we initiated these 3 award lectures, and fortunately, today, Professor Kamachi Mudali will give the KSG Das Memorial Lecture, and Professor Sagar Mitra will be delivering the S.K. Rangarajan Lecture, and the other one which will be delivered tomorrow by Professor Ratnaraj. So along with that, we also have 12 very, very special lectures by the young electrochemists all over India. So like, those will be the new trend in electrochemistry. So they will speak. And then we also have a couple of lectures by our senior colleagues, like Ningshan, he will be talking about the corrosion and molten salt electrolysis. And then Professor Shanit, who is from ISRO, will be delivering the lecture on how new energy devices will be used for space applications and etc. And then we also have the oral presentations by our budding scientists, the students and all. So overall, for next 2 days, we have very, very interesting lectures by eminent scientists and of course the budding students like electrochemistry. So along with that, we also have an MOU exchange between SICRI and Amrita Vishwa Vidyapeetham. So idea behind is that these 2 great institutes will work together, collaborate in all aspects of the R&D and education, and also any startup work or like entrepreneurship and all that. So we look forward to that closely working with the Amrita Vishwa Vidyapeetham next, in the coming days. So with that, and also I see that more than 500 delegates are here registered, and let's hope that let's wish that we'll have great 2 days of conference and at this Amrita Vishwa Vidyapeetham. And this is a place where science, technology, and philosophy, philanthropy will come together. And with this, again, wish you all a great 2 days of conference. And again, I wish you all the best and warm welcome to NCE-24.
Thank you, sir, for highlighting the role of SAIST, importance of NCE-24, and your insightful words on the importance of electrochemical science and technology. Now we request Dr. K. Ramesha, Director, CSIR Secretary, to honor our chief guest with shawl and memento. Please, sir. We request Dr. Bipin Nair, Registrar, Amrita Vishwa Vidyapeetham, to honor Professor Sagar Mitra, Guest of Honor, with a shawl and memento. Please, sir.
Thank you, sir, for doing the honors. Now, we move on to a special moment of this event. I now request our dignitaries to release the abstract cum souvenir book of NCE-24. I invite Dr. P. Raghupati, Chairman Technical Committee, and Dr. M. Pandiraj, Joint Secretary SAIST, to join for the release.
Thank you, dignitaries. It is the most awaited moment. We feel privileged to request Professor U. Kamachimudali to deliver the inaugural address.
Very good morning, distinguished Director and President SAIST, Dr. K. Ramesha, Dr. Bipin Nair, Registrar, Amrita Vidyapeetham, Professor Sagar Mitra, IIT Bombay, and who is also a guest of honor, Dr. Sasangan Ramanathan, the Dean, Amrita Vidyapeetham. From the organizer side, Dr. B. Subramanian, Dr. Andakumar, Ulaganathan, many other organizing committee members who are here from SECRI and from SAIST. My dear good friend, Dr. Professor Venkatraman, whom I know him for a very long time from DMRL days, and I see a lot of invited speakers, the delegates, invitees for this event, NCE-24. The students and scholars who have come for making presentation, as poster and oral presentations, special invitees, ladies and gentlemen. A warm welcome and good morning once again to all of you. I am extremely happy that Secretary Karaikudi and Seth Karaikudi, they come over here to this beautiful campus, Amrita Vishwa Vidyapeetham, to conduct this NCE-24. The 24th event of this national convention is an important event at the time of technology transition, the energy transition, and many things that are happening all over the country and also globally. I want to thank Dr. Ramesha for inviting me as a chief guest and also honoring me to deliver Professor K.H.G. Das Memorial Lecture. Professor K.H.G. Das is the founding president of SAST, and he has made phenomenal contribution to Secretary when he was director for a full decade. I think 10 years he was director. Today when we talk about electrochemistry, I think we think that electrochemistry is such a very narrow field in chemistry. Chemistry is ocean, and the electrochemistry is just a small island there. So we all think that what electrochemistry will play in this ocean of big chemistry. But electrochemistry has a very big role to play. Today if you talk, all of you will be knowing today in the whole country and globally, 3-4 terminologies go around, buzzwords. One is hydrogen, energy transition, or batteries, electric vehicles, the critical minerals and materials, decarbonization. All these are the buzzwords. You will hear that everywhere. The whole nation is working on, the global countries, all countries are working on this. But electrochemistry has a very big role to play. That is where if you look at the entire electrochemistry market, electrochemical market as such, if you look at the globally, it is growing at a compound annual growth rate of 8.4%, from 28 billion last year to 49 billion. It's a very astounding and phenomenal growth. By 2029 we will have in the electrochemistry market. And in that specifically if you take the electrochemical instrumentation, which is growing from 2.7 billion to 4 billion by 2034, or the electrochemical sensors, they play a major role, and they also grow from 17.8 billion to 33 billion. Means it is a field that is growing now year over year, and there is a lot of importance given because of whatever that I told about hydrogen, batteries, critical materials and minerals, and decarbonization. And electrochemistry, when you talk, okay, I can little bit dwell more on that. When you talk about hydrogen, towards energy transition, we now look for hydrogen. So what is so very interesting about hydrogen? Hydrogen is a very well-known production technology by which you have a steam methane reaction. You can always produce plenty of hydrogen, volume of hydrogen that is required, but the efficiency is very low. Then there are techniques, very conventional techniques like the electrochemical techniques using an electrolyzer. You can do electrolysis and then produce hydrogen. That is what is being utilized now for many applications all over the world. But again, the efficiency is low, and also it is an energy intensive process. So you need huge energy, and then the factor of decarbonization and carbonization comes into picture when you are going to demand energy from the fossil fuel based sources to produce hydrogen. These days, of late, you will find that a lot of new techniques, advanced techniques have come, like the copper chlorine thermochemical splitting, or the iodine sulfur thermochemical splitting of water, where you can go up to 20% efficiency, where very high tonnage of hydrogen can be produced easily. Production of hydrogen is very much required for industrial applications. It's not only for the conventional energy transition, but also for industrial applications. As a materials background person, if I would like to tell you that, the country has got a steel policy, National Steel Policy 2017, by which today we are producing about 150 million tons of steel. By 2031, this would be around 300 million tons. And by 2047, Viksit Bharat, our Honorable Prime Minister has set a target 500 million tons of steel should be produced. But for producing this steel, every ton of steel nearly 2.8 ton of CO2 is produced. This is because we have to use coal and coke as the burning agent, and also it is an energy intensive process. So if you want to reduce this CO2 production per ton of steel that we produce, let us say below 2 tons, from 3 tons to 2 tons, we have to do introduction of hydrogen into the fuel, mixing with coke and coal to start with, but later on you have to use hydrogen as a source for burning the, the mineral, and then you should get a green steel. Another option is that you can also produce by electrochemical route, that is electrowinning, that is direct oxide reduction process, DOR production process, by which oxide can be directly reduced to steel. And again, that is an energy intensive process. Unless you have a photovoltaic space energy continuously available, it will also lead to a carbon credit. So towards any industry, that way if you take, you want to make decarbonization, you want to reduce the carbon dioxide production, hydrogen plays a big role, and hydrogen production by electrochemistry route is the only option. Either it is the conventional electrolyzer based route using PV based electricity, or having the thermochemical splitting electrochemical process by which you can produce hydrogen is very important. I think talking about batteries, like selling coal in Newcastle in front of Ramesha and Sagar Mitra, they have been all working with batteries for their own entire career. There will be more speeches on this, how batteries are important today and where electrochemistry plays a major role, particularly with respect to solid state electrolytes and molten salt phenomena. We also talk a lot about today critical minerals and materials. Any material, any mineral that is short supply in our country, that we depend on another country, that is highly demanding for our application, like the rare earth minerals, that is called critical minerals and critical materials. Any metal, any material can become critical when we do not have the resources for that. For example, I will tell you, in 1980s, our country had the resource of only 60,000 tons of uranium in our country by the exploration and the mining processes. So there was a setback to our progress in the energy production, because 60,000 ton cannot work for hundreds of years. It can be exhausted by another 25, 30 years. And that is where that we did exploration, because no country will sell you that easily uranium dioxide. So we have done our own exploration. Today I am very proud to tell you that India has identified resources of nearly 4 lakh tons of, from 60,000 to 4 lakh tons. Similarly, we are in the top 5 with respect to rare earth minerals. But what is we lacking is the technology to produce these products from these minerals by high efficiency processes. That is where that electrochemical techniques play a major role. Being from the nuclear industry for the last 43 years, I am very happy to tell you that electrochemistry plays a major role. That is what I am going to speak in the KSG Das Memorial Lecture. But whether it is an analytical experiment, analytical purposes, or it is for sensing purposes, sensors, or it is for some processes like electrowinning and electrorefining, the understanding the corrosion processes, or materials production like boron carbide, the sodium production, radioisotope production, or the hydrogen production, or the basic fundamental studies on electrochemistry, nuclear industry is hugely benefited by the field electrochemistry. That is where that we gave a lot of importance to electrochemistry. I am very happy to recall that in the year 1987, we founded CEST at Kalpakam, and that used to be a very good heterogeneous junction for the chemists working on the electrochemistry aspect from various disciplines meet together and work for the application of the electrochemical technique for the nuclear industry. We had very successful conferences, including the National Convention of Electrochemists. It was there in 2007 when my guru, late Dr. Baldevraj, was the director at Kalpakam. So electrochemistry has been heavily recognized in our nuclear industry. And my own personal experience, when I was serving as the chief executive of the Heavy Water Board, we used to have the electrolyzers for the production of deuterium gas by electrolysis process. Deuterium gas can be produced by electrolyzing heavy water, which is D2O, and we used to have these electrolyzers in heavy water plant Baroda, and we used to produce this gas and sell it for the pharma and life sciences industrial applications. We also produce this boron, tetraboron carbide, which is used as the control rod material in the fast feeder reactor program. And we have established an electrochemical molten salt process by which this can be directly produced. And this process is our own innovation. We have a huge application that way for many interesting industrial applications, not only in the heavy water, but also in the nuclear fuel reprocessing applications. One thing that I would like to tell you that most of you must be from the academic and the research background. One very important message that what I would like to tell is that producing research and publishing papers, presenting your results in a conference is not is the end of your journey. Unless you translate that into a product or process for industrial application. Industrial application only will help our nation to have our own indigenous technology. Otherwise, most of our research and academic excellence ends up in giving lectures and publishing some good papers. This is what is very important, and I am very happy today because of the Atmanirbhar Bharat and the Skill Up and the entrepreneurship program produced by the government today. We have more than 2 lakh startup in our country, and I would like to tell you more than 10% of this is related to electrochemistry, thanks to the hydrogen technology and the battery technology and all this decarbonization that is being vigorously pursued by the government. Lot of young people are now going from the academic platform to the research platform to now their own industry. Having an idea is not important. Translating or converting that idea into a product, into a process by having your own entrepreneurship is the most important. So I want to urge all the younger people. I see a large number of students, research scholars and young faculties and young scientists here, that please don't stop with just presenting your work and then publishing it as a paper. And this is where that I want to tell you that Department of Atomic Energy, we never had any support from any country. Moment we had this 1974 nuclear explosion, that we have been branded as untouchable, and we were denied all the technology from the foreign countries. Today I am very proud that India is pursuing the 3-stage nuclear power program, which was the dream of Homi Jahangir Baba, which successfully completing our prototype fast feeder reactor, which was attaining critical on April 6. It is 100% indigenous technology. Everything, starting from the construction to operation, everything, all the devices, systems, more than 200 plus industries were associated with the manufacturing of all the components and systems and devices for the prototype fast feeder reactor. So all that is possible because our department trains all our young scientists to work on mission mode to make any technology, any product, any process, any device, that we have to use it in our own industry because we do not get anything from outside. So that was the demand that made us to work like that. So that is what is the message I want to tell to all the young people, that please try to do very good academic study, please do very good research, but finally you have to convert that into a product or process or to an industrial application. At least maximum whatever that is possible is to do that. That is where our country can progress, that we can attain Atmanirbhar Bharat, the Viksit Bharat by 2047. Thank you so much for inviting me, and wish the conference all the best, and I am very proud to inaugurate it. Thank you.
Thank you, sir, for the inspiring inaugural address highlighting the pivotal role of electrochemistry in meeting Viksit Bharat 2047 to green hydrogen batteries critical material extraction. May I now request our guest of honor, Professor Sagar Mitra, to address the gathering.
Good morning, everyone. Professor Kamachi Maduli from Homi Baba Institutes and Dr. Vipin Nair from Amrita Vidyapeetham and Sangsagam, maybe I am pronouncing a little differently, that's fine, this Amrita Institute, they make me, because I am Bengali anyway. So, all the dignitaries in the dais, all my friends, faculty, guests. Good morning, everyone, again. So I'm here. I really appreciate Dr. Ramesha, because he's my friend anyway. So for inviting me and giving me a memorial talk on behalf of one person to whom I worked for first 2 months during my first PhD periods. So I know him very personally, so I worked with him. And when I come for that memorial talk, this is my pleasure. Yeah, this is my pleasure to, when you say that I'm going to give a talk on that, I immediately accepted because of that reason. Okay, so I had a personal experience with him. That's one thing. So here, I won't elaborate much on whatever we have discussed. We are here for discussing electrochemistry. When I joined in electrochemistry as a PhD in IISc Bangalore, 1998, that time I joined in a Professor Sampath at IISc Bangalore, and I had to do a electrochemistry. And that time, most of the case, like from Calcutta, whoever coming to IISc Bangalore, they will be doing maybe theory or doing spectroscopy. That's our trained of Bengali should do that. So I have selected electrochemistry because not I was much interested on it, but I was interested on mathematics part of it, as well as the application part of it. That's the only reasons. And I see that I have not done the wrong decision during that time. And if you look at it, at 1998, that time to 2026 right now, electrochemistry has tremendously progressed. And I always say that SICRI is one of the, maybe the catalyst for that. And for that, I am always associated with the SICRI and anyway, wherever I can. And electrochemistry is one of the subjects right now. People think that electrochemistry is just a from solution looking at the redox reactions. It is not the electrochemistry. Electrochemistry is a combination of many topics. It's like starts with mathematics, then experimentations, physical chemistry. You are actually understanding your interface between two miscible or immiscible layers. And obviously electrical engineering, if you are studying some of the electrical part of it, like equivalent circuit part of it. So it is a bunch of many things together, and that is electrochemistry. And already previous, our chief guest already talked about it, that electrochemistry, if you look at the national mission, right now 4 or 5 topics we are looking at, where at least 3 topics are related to electrochemistry. So that we have a huge prospect for all institutes, all students who are working on this field. Try to, what is my opinion, that you try to open your mind and think little beyond whatever is already people are talked about. Okay, look at it in different way. Every problem is a problem. If you look at it, just go to the ChatGPT and look at top 5 problems which is not solved yet. Out of that 3 problems are electrochemical problems. So that is the one thing you should look at it right now. So that means we have a lot of prospects, and I hope whole 2 days, there is a 2 days, today and tomorrow, we'll be discussing many advanced level topics, batteries, fuel cell. I was looking at the brochures, many topics are there, but one thing is very common, that all electrochemistry right now, material electrochemistry, is like a materials and then electrochemistry. That's the things I was looking at it. But pure electrochemist or electrochemistry is not that. It is right now it is like we are looking at an interface, but is not of the electrochemistry. Electrochemistry is just one redox couple in a solution or in a continuum model, continuum media, and you are studying their redox behaviors or how the molecule moves, dynamics of the molecules or ions. So you should look at in different aspects. Try to read Bard and Faulkner book. I think you read 50 times, you will understand. 1 time, 2 time, you will not understand what is Bard and Faulkner's book, Electrochemical Methods. And I hope you'll understand many things out of the talks, discuss with everyone. All students, 500 students are registered here. That's a very good numbers. I congratulate the organizer, even the Ramesha, for the organizing this type of gathering where we will discuss only electrochemistry with all electrochemists. Thank you very much, and see you. Next, second talk is mine, so I'll show you again. Thank you.
Thank you, sir, for your inspiring words highlighting bigger and prospective role of electrochemistry. Now I would like to invite Dr. Shashangan Ramanathan, Dean Academics, Amrita Vishwa Vidyapeetham, to deliver the felicitation address.
Om Namah Shivaya. Well, I think Dr. Subramanian welcomed everybody. I would take this opportunity to welcome Dr. Ramesha, Dr. Kamachi Mudli again, sir. Welcome back to Amrita. The last time we saw you was in our convocation attire dress. This time you're in a different suit. Welcoming Dr. Sagamitra, and of course, Dr. Subramanian and everybody from SAIST and SECRI. This is a welcome on behalf of Amrita Vishwa Vidyapeetham representing our registrar, Dr. Bipin Nair. It's a great honor for me to stand here and give this felicitation address. I mean, everybody has talked about how electrochemistry makes a world of difference and how interdisciplinary it is. I would like to take this opportunity to actually thank SAEST for promoting, bringing this electrochemistry, the importance of electrochemistry to the world, to at least our nation at large, inspiring, encouraging the youngsters to look at electrochemistry. This is the 24th National Convention. That means it's been a long journey. Why don't we give a round of applause to the organization? Institutions like SICRI have been there for a very long time, pioneers in electrochemists, and I should thank SICRI for actually educating a lot of our faculty. A lot of our faculty have graduated from SICRI, and they are here, and they've been part of this whole journey on advanced research, and I should thank SICRI for that. It's very important that we understand that when we are pushed to a corner, we come through, and we come through it in a big way. ISRO and BARC and Homi Bhabha Institute, they had no support from anybody. You know, when there is technology available, we can buy, we take the easy route. We have been as India. But when you don't get technology from outside, we can beat the entire world, and we have proven it time and time again. Now, what do we do? Dr. Kamachi very nicely said, product development. I mean, we have a lot of basic research done, we publish, and we accumulate a lot of papers. But how many products are out there from India that says made in India with a beautiful lion sign and says, I will compete with US products, with the Japanese products, with the South Korean products, Singapore products? How many products are out there? You can chat GPT and find out. Our manufacturing is quite good. But are we competing at a product level? So, as youngsters, I'm telling you today, research in the lab is not going to be sufficient. You have to translate that research from the lab into a product, which means your thinking must be more system level. Think system level when you start your research. As eminent electrochemists, I'm going to challenge all of you one time, because you won't see me at least for the next 2 hours, so I don't get beat up. How many of you think copper electrochemistry, electroplating is a huge challenge? Every one of you will think, copper plating, that's been known, we can plate anything and anywhere. No big deal. Copper electroplating is not a big challenge, right? I beg to differ. I beg to differ. what you buy in chips in your mobile phones, laptops, and even in your big servers now, that's a big thing. Every one of those chips has kilometers of copper. And I'll give you an example. I'm going to pull a hair, which is not my hair, which is quite short, 30 centimeters. I'll keep it very short, sir. 30 centimeters of hair. Very nice. You drill a hole which is 0.5 millimeter. Okay. Let's say I solved that challenge of drilling because it's been solved. 0.5 millimeter hole, 30 centimeter hair. How are you going to plate copper into it? Let's say it's conducting. All your parameters, electrodes, everything is given. Can you uniformly plate inside that hole using copper? Now you take that challenge. Why am I saying this? Anything that you think is a basic research and it's advanced and we are done with it, when you start looking at product, it has its own list of problems, challenges, reliability, the challenges of how to do something given a set of constraints. Those things come when you talk about product. So I'm telling you today, copper plating has a lot of challenges, starting from plating to recycling the slurry, to recovering your metal, reusing it. All this is carbon footprint. So you're looking at a holistic picture of starting with a simple process to a product to sustainability. This is how your thinking must go as young researchers. When you do that, and when you can come up with products that has that, the pride of made in India, make in India, we will shine. And I think I should thank SAIST and SICRI for choosing Amrita to host this beautiful convention, this national convention, and we will have more of these in the future. And I wish all of you the very best. Interact, think system level, think product. Now, this should be the kind of things that set into your mind. And I thank all of our esteemed people who are going to be giving talks here. Please share your knowledge and let's all network together, solve grand challenges that translate into Atmanirbhar Bharat. With that, I will once again welcome and thank every one of you for attending this national convention. Om Namah Shivaya.
Thank you, sir. CSIR SICRI and Amrita Vishwa Vidyapeetham, the premier R&D and academic institution, have been working together through academic collaboration. To further strengthen this, CSIR SICRI and Amrita Vishwa Vidyapeetham is signing an MOU on this important occasion. Now, I request the officials from CSIR SICRI and Amrita Vishwa Vidyapeetham to exchange the MOU.
Thank you all. May I now invite Dr. A.K. Nandakumar, Associate Chair, Department of Physics, Amrita Vishwa Vidyapeetham, Co-Convener NCE-24, to deliver the vote of thanks.
Good morning. On behalf of the organizing committee, it is my pleasure to thank many people here who have been responsible for the success of this inaugural ceremony. It's a pleasure to thank, starting with the chief guest, Professor Kamachi Mudali, who has come over all the way from Bombay for this inaugural ceremony. Professor Sagar Mitra, our guest of honor, from SECRI, Dr. Ramesha, who is also the president of SAIST and also the director of SECRI. I would also like to thank Dr. Bipin Nair, our registrar, Dr. Shashankan Ramanathan, our dean of academics. I understand that on behalf of the organizing committee, we appreciate that all of these are people with a lot of administrative responsibilities, but they have made time to come over and inaugurate this function. Thank you all. I would also like to thank the head of the TTBD section, Technology Transfer and Business Development section of SECRI, and the Corporate and Industrial Relations Department of Amrita, who were responsible for the smooth transfer of MOUs, exchange of MOUs. A big word of appreciation for them. I would like to thank all the sponsors of NCE-24, whose stalls are put up outside. Eventually, I will come across those. Thanks to all the sponsors. And I would also like to thank all the principals of various schools of Amrita, the heads of departments of many departments who showed a keen interest and cooperation in this joint convention, all the scientists, faculty members, students, participants, and all the committee members whose cooperation has led to a very smooth inauguration, and hopefully we hope that you will have a very pleasant and enriching experience for the next 2 days here. Thank you.
Thank you, sir. With this, we come to the end of the inaugural event of NCE-24. May we request our esteemed dignitaries to kindly take their seats off the dais as we proceed with the technical session.
Okay. You wrote something here? Okay.
Now we request Dr. K. Ramesha, Chair, to present the citation to Professor Kamakshi Mudali, please. Yes, sir.
It's an honor for me to read this citation. So I told the students that I myself would like to read this. Society for Advancement of Electrochemical Science and Technology, National Convention of Electrochemists NCE-24. Proud to honor Professor U. Kamakshi Mudali with the Professor K.S.G. Das Memorial Lecture Award 2024. The Society for Advancement of Electrochemical Science and Technology, in brief, like we call as SAST, is proud to honor Professor U. Kamakshi Mudali with the Professor K.S.G. Das Memorial Lecture Award 2026 in recognition of his pioneering contributions over the past 4 decades in advanced materials, coating technologies, electrochemistry, corrosion science and engineering for nuclear and allied industrial applications. Professor U. Kamakshi Mudali is the Distinguished Vice Chancellor of Homi Bhabha National Institute, Mumbai, a premier deemed university under India's Department of Atomic Energy, a globally renowned metallurgist and corrosion expert. He assumed his leadership role in May 11, 2023, bringing decades of pioneering contributions to materials science for nuclear and other extreme environments. Dr. Mudali's journey began with an M.Tech in corrosion science and engineering from IIT Mumbai, rank holder, and a PhD in metallurgy corrosion from Madras University in 1993. His academic fervor fueled his lifelong pursuit of innovative solutions in corrosion-resistant materials, especially for India's atomic energy program. Prior to joining Homi Bhabha National Institute, he served as a Vice Chancellor of VIT University, Bhopal, that is 21 to 23, Honorary Professor at IIT Madras, 21 to 22, and Chairman and Chief Executive of Heavy Water Board, Mumbai, 2017 to 20. His leadership qualities are well recognized by the participation in various committees of Niti Aayog, BIS, AICTE, ISCHE, NACE, India. Dr. Mudali was the president of Indian Institute of Metals, Kolkata, NACE, India, and Asia Pacific Area, ISCHE, MRC, Mumbai, and ECSI, Bangalore. Dr. Kamakshi Mudali, in his career at Indira Gandhi Center for Atomic Research, IGCAR, Kalpakkam, 1984 to 2017, pioneered in advanced alloys and coatings, enabling sustainable technologies in harsh conditions, and led various R&D projects relevant to fast breeder reactor program. He was the Director of Materials Chemistry and Metal Fuel Cycle Group at IGCAR. In Homi Bhabha National Institute as Senior Professor, he mentored nearly 162 students of various institutions in different UG and PG programs, including 12 PhDs. With 477 plus journal publications, 25 books, 5 patents, and 350 plus invited talks, his works boast 15,300 citations with an H index of 59 and I-10 index of 325. Dr. Mudali was honored with the Lifetime Achievement Award by the Ministry of Steel, National Corrosion Council of India, that's the last time I remember, NCCI, and Electrochemical Society of India, and as a distinguished alumni of both IIT Bombay and PhD College of Technology, Coimbatore. Key accolades include Homi Bhabha Science and Technology Award, DAE, and Distinguished Faculty Award, G.D. Birla Gold Medal, IM Platinum Medal, and Meritorious Award for Corrosion from NACE and NCCI Karakudi. It is worth to mention Professor Kamakshi Mudali is the first Indian to receive the Frank Newman Speller Award from NACE in 2019. So Dr. Mudali is a fellow of 13 academic societies, including 5 from abroad. So with this citation, it's a great honor for me to bestow the K.S.G. Das Memorial Lecture Award 2022, Professor Kamakshi Mudali. Thank you, sir. request you to deliver the award lecture.
Thank you.
Thank you.
I think the lecture should be loaded. You can open from the pen drive directly. There is only one file, presentation. Very good morning, and thank you so much, Dr. Ramesha, for honoring me with this prestigious Professor K.S. Das Memorial Lecture. And as I mentioned, that in 2007, the same lecture was delivered by late Dr. Baldev Raj at Kalpakam when the National Convention of Electrochemists was conducted. And I was a young scientist there, observing and watching the presentation. And today I'm really feeling that destiny has given me the opportunity to deliver the lecture by myself. And thanks to Secretary, thanks to SEST for giving me this opportunity and honoring me. So what I'm going to speak in the next 45 minutes is a lecture, 30 hours of lecture that I take electrochemistry and nuclear technology course in Coimbatore National Institute sometime back when I was a senior professor. So I'm trying to condense it. And I want to give an idea to all the young, bright students and scholars that it is not electrochemistry, just nothing, something you can do, only electroplating or some small work in the laboratory. It has got a wide variety of application for a mission program like Department of Atomic Energy. And that also I am focusing only on the electrochemistry related work done at fast breeder reactor research. And if you take the entire, the Department of Atomic Energy, it's going to be a phenomenal, it should be a course on that. So I'm trying to give an overview, an essence of the different aspects of the application of electrochemistry for a product, for a process, for some application directly in the Department of Atomic Energy in the fast breeder reactor program. And my homage to Professor K.S. Das, the founder president of SEST, and also the director of Secretary for about 10 years. And it is my honor and privilege to deliver this memorial lecture by Professor Das. Is an outstanding electrochemist, well known internationally for his original and innovative contributions to both fundamental and applied aspects of electrochemistry. He has made remarkable achievements as teacher, mentor, and administrator, and is a role model for the youngsters pursuing electrochemical science and technology. With minimum experimental facilities and funding available, Professor Das has shown to the world that excellence in science could be achieved. I am very proud to dedicate this memorial lecture on industrial application of electrochemical processes in closing the nuclear fuel cycle to these pioneering electrochemists of this nation. Let me give an introduction that today, energy is a very important requirement. With respect to global scenario or Indian scenario, energy is the most important thing that is required. Without energy, we will not be able to make any progress in the society or industry and public. Today, if you look at 4.3% is the electricity demand year over year. By 2024, you can see this is the total energy demand 2.2. GDP was growing at 3.2. And the electricity demand was 4.3%. And out of this energy that is produced in 2024, you can see renewable natural gas and they are taking the predominantly the 38% and 28%. Coal and oil are taking only 26%. Global energy is produced 8% nuclear, but unfortunately India we are only producing less than 3%. Our progress is not as it is anticipated due to various constraints. India's power generation is projected by 2047 Viksit Bharat, that is 708 gigawatt electricity, which is almost double, fourfold increase that we have to increase to 2100 gigawatt. So we have to increase the installed electrical capacity today, what is available, by 6 times. Today it is around 400 gigawatt. So we have to increase by 6 times by 2047. But we should also have, like the global thing, we should have 78% share from non-fossil. That is the target of the government. So 50% of the power capacity should be at least by non-fossil sources. And we should reduce the emission industry by 40% by 2030 in order to achieve net zero emission by 2070. That is what, if you look at the Niti Ayog's Viksit Bharat 2047, the target that is set. It is now the government has set up a target for the nuclear power that it should be 100 gigawatt by Viksit Bharat 2047. So we have to produce out of the 2100 gigawatt, 100 gigawatt through the nuclear power. And today if you look at the rest of the world scenario and the other countries, India is the biggest producer of the fossil fuel based power. If you look at here, the renewable, nuclear and the natural gas is very insignificant. Compared to the global average, you can see here the fossil fuel is significantly reduced. It is around 28%. You can see the rest is by the renewable and nuclear. Nuclear is 8%. Whereas look at other countries, look at China here. China is, constantly they are working on increasing the renewable and decreasing the fossil fuel. Countries like you can see European Union, the coal is almost, around 10 to 12%, and the United States is around 15%. So we have a very big target set to increase nuclear and renewable and reduce the coal. And towards this is what is the government of India's target that is set from today, 2020, from today to 2047. You can see that the green one, that is the renewable and the clean energy should increase tremendously, and we have to also reduce the coal-based power by 2047. Coming to this 100 gigawatt by nuclear power, India is pursuing its nuclear power program, which is more than 70 years old, through a 3-stage power program. This is the vision and dream of Homi Jahangir Baba. In the stage 1, we produce power primarily by pressurized heavy water reactor, where we will be able to build the fissile inventory, that is plutonium. Uranium oxide, which is naturally available, natural uranium oxide is used as a fuel in the pressurized heavy water reactor, and the unused uranium and the plutonium that is produced in the reactor, which is a man-made element, both together will be put into the plutonium fueled phosphate reactor that is coming up at Kalpakam, where the plutonium can be recycled and breeding will take place. Then we can introduce thorium at this stage in the peripherals of these reactors. So you produce enormous uranium-233. That becomes a big inventory for the 3rd stage, where directly thorium and uranium-233 can produce 155,000 gigawatt electricity a year. That is going to be the biggest energy resource for our country. So from stage 1 to stage 2 to stage 3, we have been taking quite a lot of time, because the whole technology has to be mastered, right from fuel to reactor utilization, reprocessing of the fuel, spent fuel, reutilization, recycling it, and then putting thorium, processing it, and producing an inventory of uranium-233, then going to this. Though we have produced successfully nearly 20 pressurized heavy water reactors in the country today, with majority of the power coming from the pressurized heavy water reactors. Today, I am very proud that the PFBR at Kalpakam, prototype phosphate reactor on April 6 attained criticality, which is a 500 megawatt one reactor, and subsequently 2 more such reactors will come at Kalpakam with time. The third the stage is experimentally proven. We have a reactor called Kamini, Kalpaka mini reactor, which is already operating with uranium-233 fueled research reactor. So the technology is proven for all three, but making it into realistic situation is taking time. If you look at a nuclear power plant, how that it operates, basically you have the fission reaction happening here with the nuclear fuel, and the heat generated is converted to steam by making the water to become steam. Then by operating the turbine and generator, you make the power. Then the steam is condensed using a condenser, where we need continuous source of a huge quantity of water. That is where the power plants are set by the side of a lake, river or sea, coastal atmosphere. Then this condenser condenses the water, and again it comes to the reactor core where fission is happening, heat is generated, and the heat converts this water into steam. So this is the way the nuclear power plant is operating. I am proud to tell you that India has got 4 different types of nuclear power plants operating in the country. We have, as I said, pressurized heavy water reactor where natural uranium oxide fuel is used. Then we have a boiling water reactor at Tarapur. In fact, the world's longest serving, 55 years continuous operation, the boiling water reactor at Tarapur is belonging to our country. Then we have pressurized water reactors. We have all the nuclear submarine that is operating in our country is with the pressurized water reactors. We also have a commercial 2 VVER type pressurized water reactor at Kodangulam, which are producing 2 into 1000 megawatt power generation. Now currently the PFBR, the prototype phosphate reactor at Kalpakam, which has attained criticality. All 3 other reactors are based on water, so they are all based on heavy water or boiling water or pressurized water reactors, whereas this reactor is an entirely different technology. It uses liquid sodium as coolant, and it's a high temperature reactor, high efficiency reactor. If you look at the pressurized heavy water reactor scenario in our country, we started in 1970s with the Ravatpeta Atomic Power Station 1 and 2, and then by forming the Nuclear Power Corporation of India in 1987, we made an excellent roadmap. The 220 megawatt reactors we improved and then enlarged to 540 megawatt at the Tarapur Atomic Power Station, and today we are operating 700 megawatt reactor. This is entirely from 220 to 540 to 700 by the indigenous technology, and no other countries involved in this. And today we are masters of making the 700 megawatt reactors. So our capacity today from 8,880 megawatt to 22,480 megawatt by 2031, they are tripling the present quantity only by adding 15 pressurized heavy water reactor, the PFBR 500 megawatt at Kalpakam, and 4 more 100 megawatt VVER type at Kodangulam. In fact, I think in this year 2026, the 3rd unit of this 1000 megawatt is going to be commissioned, and 4th unit will get commissioned in 2027. Our reactors, will number today from 2026 as 24. By 2031, it will become 50. That is a phenomenal growth that we will have to jump from 8,880 to 22,480. And the capacity will further increase from 22,480 to 1 lakh megawatt, that is 100 gigawatt energy by 2047, Viksit Bharat. How this will be achieved? In addition to NPCL setting up number of reactors, we are going to have additional foreign collaboration with Russia, France, like at Kodangulam, at Jaitapur, at many places. The government PSUs today, like the NTPC, the GAIL, and private partners like Adani, Reliance, they also will be permitted to set up this nuclear power plant with the support of the NPCIL. So towards this, a Shanti Act has been already passed by the government in the parliament, and this is going to make all this contribution from 22.4 gigawatt to 100 gigawatt by 2047. This is the second stage, the sodium cooled fast reactor and fuel cycle facility at Indira Gandhi Center for Atomic Research. We already have a fast breeder test reactor operating since 1985. It is a 13.5 megawatt electricity test reactor which uses plutonium carbide, uranium carbide fuel, and this, the generation of power and excellent performance has already been achieved, and we are going for APTR 2 with metallic fuel, which is under design and approval by the government. After this, the 40 megawatt thermal, 13.5 megawatt electrical fast feeder test reactor, today this PF that is critical will be producing power this year, end of this year. By the first quarter of the 27, it will attain the full power, and this is the greatest achievement for the Indian country. After this, we have two different routes, duplicating the same to two different reactors, twin units at Kalpakam, and then we will, in the meantime, doing a metallic fuel activity. Currently, we use uranium-plutonium mixed oxide fuel, but in future, we will go for uranium-plutonium, zirconium, metallic alloy fuel project, and that will be 1000 megawatt, and this also will be set up indigenously beyond 2031. This is all based on already the experience and the expertise that we have achieved by operating this APTR and by setting up this PFBR. This is the stage 2. And if you look at the general nuclear fuel cycle, it's it is having different technologies and facilities and units spread over our whole country. See, first of all, you should have the uranium fuel. So we have to do mining and milling of the fuel mineral that you get, and we get finally a uranium LA-quake, that is U3O8, which goes to the fuel manufacturing plant where it is getting converted to oxide UO2. This UO2 will go to a fuel producing unit where either UO2 will be used directly, or it will be enriched, or UO2 will be mixed with PuO2, or this will be converted to uranium carbide and mixed with the plutonium carbide. So 3 different types of fuel are today used, and the 4th one will be UPU Jatar metallic fuel that will be in the future. Now these fuel are used, and the reactor operates, and the efficient reaction produces heat and energy, and that is what is producing the power by operating the turbine, and then the energy that is produced, power that is supplied to the thing. So once the reactor power reaches its different stages, the fuel bundle will be removed, and that goes for chemical reprocessing. So in a nitric acid based plant, the spent fuel is undergoing processing. The radioisotopes that are produced, that will be taken out, and that will be going for various industrial application, medicinal application, agricultural application, and the waste solution will be processed and stored in geological display. What is very important during reprocessing, we take out the plutonium that is produced, it's a man-made element that will be sent to the fuel plant for further use, and the unused uranium that has not undergone fission will be taken out, and again it will be converted to uranium oxide or uranium carbide, and it comes back. So this is a fuel cycle, that is nuclear fuel cycle that India is adopting. This is called closed nuclear fuel cycle. Now I come to the topic that where is that electrochemistry comes into this picture. You can see here I have put different sectors in which the electrochemical science and technology is used. Number 1 is in the reactor system, the controlling the water chemistry, the pH and gas sensors that are used not only in the reactor but also in the heavy water production, the H2S sensors, hard chromium plating that is required for various operating components where electrochemical deposition is used, hydrogen meter to measure the presence of hydrogen in sodium and cover gas for the prototype fast feeder reactor, carbon meter to study the level of carbon in liquid sodium. These are all in the reactor system. In the reprocessing of the spent fuel, we use a number of electrochemical processes: electrooxidative dissolution, electrolytic conditioning, electrolytic partitioning, electrolytic uranous production, electrowinning and electrorefining in molten salt. So these are the techniques in the reprocessing of the spent fuel. Then in the processes, various processes in the entire nuclear fuel cycle, for the process control we use electrochemistry using potentiometry, amperometry, polarography, and a number of their derivatives too. In the analysis part, for nuclear material accounting, potentiometry, amperometry, and polarography and the derivatives are also used. Electrochemical material science plays a major role in the entire nuclear industry, not only for production of the special materials like boron carbide, the control rod material, and liquid sodium, nuclear grade liquid sodium, but also the production of various electrocatalytic coated electrode materials for the electrochemical processes in the reprocessing, like the mixed oxide coated titanium, mixed oxide coated titanium anode glazed, and the plasma modified mixed oxide coated titanium anode is a patented process, and we use it successfully today also. The polarization and impedance analysis, electrochemical noise analysis for the corrosion testing, evaluation and monitoring. In the waste management, when the solution that is coming after recovering all the wealth, radioisotopes, we have to do the waste volume reduction, for which we use electrolytic decontamination and electrolytic acid killing for reducing the concentration. We do the destruction of organics and resins that are present by electrochemical techniques, and we also separate whatever trace amount of actinides that are left using electrochemical techniques. So this is the entire spectrum of the electrochemical techniques. I am just going to give a bird's eye view of some of these techniques that you can understand. Sensors play a major role in the nuclear fuel cycle, entire nuclear fuel cycle, right from the mining of the fuel to the spent fuel storage and waste management facilities. The various types of chemical sensors, conductivity sensors, the eddy current, the non-destructive sensors, thermographic sensors, ultrasonic sensors, radiation sensors, laser-based sensors, various sensors being used, and entire sensors we make ourselves and we produce ourselves in our nuclear labs, and then we use for this application. Coming to specifically to the fast feeder reactors, we need to detect the level of sodium, we need to detect the impurities in the sodium, we need to see the flow of the sodium. All that is being done by various sensors here. The most important is when there is a possibility of a nanogram of sodium interacting with water or steam, that can produce exothermic reaction. That's a very dangerous reaction that cannot be allowed. So we need to sensitively monitor for hydrogen, because once there is a single molecule of sodium interacting with the water molecule, it produces hydrogen, and the hydrogen we can detect up to parts per billion levels using our sensors. That's a very important thing. Then we have radiation sensors, sodium aerosol sensors, and then you can see here different family of sensors based on mutual inductance, eddy current, sodium ionization detection, delayed neutron detection, in addition to the electrochemical sensors for detecting carbon, detecting hydrogen, detecting oxygen in the fast feeder reactors. So as I mentioned, see this is a tube, that is sodium is present inside the tube, inside the big tube, and you have smaller heat exchanger tubes where inside water is coming, and that becomes a steam. In case of any leak in this tube, sodium can react with the water, and that can lead to sodium hydroxide and hydrogen production. So to detect this hydrogen parts per billion, we have used hydride ion conducting calcium bromide, calcium hydrobromide electrolyte. This is the electrolytic system here, and this has been arrived after studying so much of the phase diagrams. And for example, you can see under normal operating conditions of the reactor, up to 13 parts per billion resolution we can detect this hydrogen. And you can understand, even at very high temperature of 450 degrees, the reactor operating sodium temperature, we can detect the limit of 50 parts per billion. And these sensor probes have been attached in our reactor, not only the reactor but also in the facility like sodium, the steam generator facility. And very important is, with international collaboration, we have put our sodium and the hydrogen meter in the Phoenix reactor of France in October 2007 to see its entire performance in the plant operating condition. So what is very important for the young people, that we do also the the academic research, we do the R&D in the laboratory, we do also develop a lot of sensors, but we stop with the sensor. We stop with writing a paper or presentation on that. What we do further, the sensor is made into a product. The product is tested in the lab, and calibration is made, standardization is done. Then it is put into pilot plant lab scale facility. Then it goes to the actual reactor, and that is where you can close the entire the TRL, your research level from the product that is coming, and you can do the demonstration that how accurate, sensitive is your hydrogen detection when there is a injection. Artificially you inject sodium into the steam into the sodium or water into the sodium. We have also made a hydrogen sulfide sensor for the heavy water plants. The heavy water is produced by the isotopic exchange between hydrogen sulfide and water. So we use, you imagine, the two streams of the heavy water production plant in Managuru, 400 tons of hydrogen sulfide, 400 tons of hydrogen sulfide. You know the limit, the TLD limit is that 5 ppm, that somebody will meet a fatal situation. So our sensor has the capability of detecting that, since it is not a nuclear directly, we get the sensors from foreign countries. Now there is a requirement of more heavy water for increasing our production. So there is going to be a denial regime. They may not supply us these sensors. So we have made these sensors compared to the currently operating sensors in the plant. We put our sensor that was developed in our Indira Gandhi Center for Atomic Research. This is basically a tin oxide, copper oxide waste thing. So two of these modules that we have made, we put along with the commercial one, and we have found a matching performance of these sensors. So we are going to now use all the future heavy water plants, the indigenously developed, the laboratory tested and prototype that is made, applied in the plant. Now we are going to duplicate it, or we are going to find a vendor. We are going to produce ourselves in our Electronics Corporation of India Limited, ECIL, and use it in the plant. There are other related, cover gas hydrogen monitor. This is the temperature is maximum is about 250 degree. The oxygen content in the ambience of the sodium reactor is very important. Ingress of moisture is going to be a dangerous thing, because anytime this water can condense and it can get into the system, that can lead to problem. So we maintain a positive pressure inside the control room so that no moisture enter into that. So to monitor that, the oxygen has to be sensed, detection limit of 1 ppm oxygen in the operation area. We also have an electrochemical carbon probe, because carbon can get into sodium through the oil leak into the sodium or any other way that it can do that. So we have these sensors are also now operating in the test reactor. So this is the family of such sensors. We don't stop with the research. We make all these products, we standardize them, calibrate them, and we get it qualified, certified, and these sensors are being directly used in the reactor application. Today our fast breeder reactor is operating entirely with these detectors and probes that are used. The second important thing is that, as I have told, the fast breeder reactor requires 1,700 tons of liquid sodium for 500 megawatt reactor. 1,250 will be in the reactor, additional 400 ton will be there outside. So this is a recirculating loop. So this sodium is now becoming a critical material for us. The only country which produces nuclear grade sodium today in the world is China. And any day China can either jack up the price or they can deny, like they have now denied giving fertilizer to our country, which is a common material. So that as fertilizer has become a critical material for us. We are trying to get from the Arab nations, we are trying to get from China, Russia. So sodium has to be produced. The production of sodium is a well-known technique. All of you know the Downs process, where you can do the electrolysis of a brine, you can take sodium. So that is as simple as that we can tell. But what is the important thing is that producing a nuclear grade sodium is the most important thing, because you will have very high level of carbon, calcium, magnesium and oxygen and iron. If you use such a impure sodium, this will undergo radioactive reaction, and that will spoil the whole fast reactor power spectrum. So we cannot allow these impurities. So we need to produce sodium in industrial scale, and also we have to produce the sodium in nuclear grade. So we have set up a plant at a heavy water plant Managuru, which is operating with this basic Downs process, and this process is going to right now we have a 2000 ampere cell. This is the Downs cell, and the sodium that is produced come to the storage tank, and then we have set up this plant and operated and produced 7 tons, and then sent to IGCAR Kalpakkam for application, and qualified this for the reactor application. And then now we are setting up 24 kiloampere, that is 2000 to 24,000 ampere cell we have designed, and with this this operator at an efficiency of 50, and we are now expecting this 12 number of this 24,000 ampere each one of them will, with 50 metric ton, it will produce 600 metric ton per annum. So if you operate for 3 years, then we will get sodium that is required for one reactor. So if we set up one more facility, then we can increase it and cut down the time also. So the cost also we have worked out, which is about 850 rupees per kg. So this is a very important requirement, and these are the parameters that we have almost optimized. And what is very important, you can see the requirement. This is the nuclear grade sodium requirement, and we have met all the parameters, and in fact some of the parameters are much better than what is required. We can get 2 ppm of iron, and you can see 1 ppm of magnesium, and all these are all, we don't want this to be present in the sodium. Then the boron that is required for the phosphate reactor is a control rod material. Where electrochemistry varies, it coming into picture. We have electrowinning cells operating at the heavy water plant Managuru, where the KBF4 conversion, the PF3 ether that is mixing with the potassium to produce the potassium fluoroborate, and electrowinning of that produces boron carbide, and this boron carbide powder is made into pellet, and that is used in the phosphate reactor for controlling the reactor. And this is an, normally it is produced by the molten salt electrolysis of KBF4, KCl, KF mixture, and these are the reactions, and we have already produced so much of quantity for application in our reactor, and this is the electrowinning facility that is at Managuru. You can see that this is the basic principle of the boron electrowinning cell. We have about, I think operating is about 8 numbers, but 12 number of cells are set up in Managuru. These are the final boron carbide pellets that are used to assemble and make the boron carbide control rod. But one important thing is that in the end of life of this boron carbide control rod, the unused boron has to be retrieved back. This is also very important because we can't throw it as a waste because it's very expensive. So we also technology to produce this from boron carbide to boron back. So electro-oxidation of boron from boron carbide. We have made a process, but it is yet to be upscaled to operating in pilot plant. It will take a longer time. Coming to the reprocessing, which is very important, which is where the spent nuclear fuel is undergoing chemical processes like dissolution, clarification, partitioning, extraction, decontamination, reconversion in a nitric acid based medium. This is called Purex, that is plutonium uranium reduction by extraction process, aqueous reprocessing. Another, for the metallic fuel, we follow molten salt pyrochemical reprocessing, where electrorefining is the heart of the entire thing, where we can convert the spent fuel, that is uranium, plutonium, zirconium, with a lot of minor actinides, fission products and sodium, into uranium and zirconium and plutonium separately for making fresh fuel. These are the 2 different routes we are following it up. In the aqueous reprocessing, we have a phenomenal, we have very large number of the processes that are being used, as I have already mentioned, and not only the processes optimization and utilization for the plant scale, but their structural materials and the dimensionally stable electrodes that are required for these electrochemical processes are also very important. So why it is so important? Because the fuel is ceramic in nature. Uranium plutonium oxide is highly noble in nature. Dissolving it in a conventional any chemical solution is very difficult. So we use 11.5 molar nitric acid under boiling condition. We also use a number of electrocatalysts like silver electrocatalyst or cerium electrocatalyst for enhancing the reaction at the anode for the dissolution of the fuel into its soluble state in the nitric acid. So we have designed and developed a dissolver exclusively for that. We have developed the electrode material for that. The process has been developed. So at a time, 1 kg of the spent fuel can be used in such a dissolver, and we can continue the processes directly for the production. There are a large number of electrochemical reactions that will be happening. One of the advantages of electrochemical processes is that by excellently controlling the electrochemical potential, you can always try to separate any one of these, the element that is to be separated from the solution. you can do the electrochemical method, because electrochemistry plays not only in the dissolution and conditioning, but also separation of not only uranium and plutonium, but so many other valuable radioisotopes. And once we finish the reprocessing, the high level liquid waste that is accumulated, which is highly concentrated, which contains also a lot of very hazardous, the ions. So to destruct that, to destroy this hazardous nature, to reduce its concentration, we have designed and developed an electrochemical cell where electrolytic acid killing can be done, by which, and you can see that by which at the anode hydrogen can be generated, and several other the nitric acid based reactions can happen as a reduction, and we can reduce from 4 molar to 0.01 molar concentration. Once it becomes dilute, it is very easy to now handle it in a conventional evaporation technique. So we need these electrodes. These electrodes should be highly conductive, electrocatalytic activity should be higher, and they should have very high corrosion resistance. The conditions of electrolysis will involve nitric acid from dilute to concentrated condition, room temperature to boiling, and most of the time this medium contains also various fission products, electrocatalytic ions like silver and cerium, chromium and iron from the structural materials. So we need the dimensionally stable anodes, which are basically mixed oxides of the noble oxides coated over the surface of wall metals like titanium, tantalum and so on. So we have developed 3 different types of the oxide coated. One is the oxide coated family, another one is the metal coated family. I will give a brief example of it. The strategy is that it is well known, the TSIA, what people call SECRI has developed long back, that the titanium substrate insoluble anodes, which are used in the chloroalkali industry, where brine electrolysis is done up to 80 degree, it works excellent. Whereas for 11.5 molar nitric acid and boiling condition, it is very difficult to use these electrodes because they fail after 80 degree. So what we have done strategically, we introduced a very thin conducting layer in between here, non-stoichiometric layer, over which we put a noble metal coating. So this has become an excellent, otherwise what happens is, once you have such a thing, they form a thick transition insulating oxide, and this is not acceptable. So not only the strategy of making such an interlayer, but also the conducting surface on the top with noble metal, electrocatalytic activity, corrosion resistance, longer life, resistance to short circuit. These are important parameters that one need to work before developing such electrodes. And this is the method of preparation, the flow sheet, mechanical and chemical treatment, coating composition and structure, preparation and application of the coating solution, coating development treatment. All this has to be optimized, and we made an Indian patent in 1997 to produce this DSA category of ruthenium dioxide 40%, titanium dioxide 60%, with or without an overlay of platinum oxide on the surface. This is the entire flow sheet for this preparation of these electrodes. So the first category was developed by thermal decomposition of the salt of ruthenium and titanium, where we get a cracked mud morphology of the mixed oxide of ruthenium and titanium dioxide. But unfortunately, it works only up to 215 hours in an electrolysis. Then we developed over this platinum oxide glazed coating, and that worked, I think, up to 1840 hours. But not satisfying with this, we have made also a plasma modified Mokta coating, by which controlled oxygen is supplied through a DC reactive oxygen plasma, and that worked also 1460. So compared to the conventional oxide coated electrodes, which can work only up to 200 hours, these electrodes, which are innovative in nature, they can work up to 1800 degree without failure. So these are the electrodes that are used today. But there is always a question that why we have to use an oxide coated electrode, why not a metallic coated electrode? So when we use electroplated platinum, what is happening is that once we use into the service, the coating fails by opening up at different defects, and different, due to the electroplating, you have a lot of defects and the coating opens up. So this fails in service very short time. So what we have done, we have given an interdiffusion treatment between titanium and electroplated platinum, and even there is a failure of the platinum coating, this interdiffusion layer will help a longer life. This heat treatment is been designed by looking at the allotropic phase transmission temperature of titanium, and this is done after platinum electroplating at 1100 degree. And this diffusion alloying treatment produces an excellent interdiffusion zone. You can see here, this is the platinum plating, this is the normal titanium, and this is the interdiffusion zone where platinum is diffused. And this gives an excellent performance in the rate determination measurements, and this is one of the alternate opportunity that is available. Recently, one of my PhD student, just about, she finished it a few years back, and we tried innovative platinum nanoparticle coated titanium TiO2 nanotube. We took 4 different routes. In the route 1, hydrothermal reduction of platinum, route 2, cyclic voltammetry and electrode deposition of platinum on the surface. Then route 3 is electrode deposition and then followed by hydrothermal reduction, and route 4 is development of a TiO2 on titanium, then electrode deposition followed by hydrothermal reduction. The route 4 became the successful one. So we developed electrode deposition of the platinum particles on a titanium dioxide, the nanotubes, and over that also we put the hydrothermal reduction of platinum, and that gave an excellent performance. The electrode deposition directly followed by hydrothermal, and the nanotube formation, then electrode deposition and hydrothermal, which gave by the CV studies and the life analysis the best performance to be used for future. And you can see here the electrodes for a pilot plant was made, and we checked and we found that the platinum nanoparticle loaded titanium nanotube worked up to 1750 degree compared to platinum nanoparticle coated titanium 1150 degree. Not only that, we also evaluated their surface coverage, adhesion to substrate, mechanical stability, electrocatalytic activity, and we found that platinum nanoparticle coated TA nanotube is the best one. Whereas in the previous oxide coated, you have to give a heat treatment at 500 degree or 1100 degree, which is very difficult to do in a radioactive environment. Whereas here the application is within 100 degree, so we can do easily in a radioactive environment if we have to recoat and use these electrodes for further application. So number of these electrodes have been produced, and they are all used in the plant. This is what I want to tell the young students and scholars, that it doesn't stop with paper. You could have seen that I mentioned several publications made, but they all go into application in the plant. These electrodes are qualified and used in the plant. The second one is the pyrochemical reprocessing, where I said the electrode refining is the heart of it. The metal fuel will be put into solution in a molten salt solution, you can see here. And there are a number of techniques: oxide electrowinning, the plutonium electrorefining, direct oxide reduction, and then demonstrating all of them in the bulk processing. This is what is done for the pyrochemical reprocessing. And basically, you take the spent fuel in a basket, put it into molten salt at 500 degree of lithium chloride and potassium chloride. Then you have two different cathodes. One is solid cathode, graphite or steel. The second one is a liquid cathode. The liquid cathode is cadmium here, and you will adjust the potential current conditions such that the uranium is completely deposited on the first cathode. Then the remaining solution is electrolyzed again with liquid cathode as the cathode, liquid cadmium as the cathode, and the remaining uranium, plutonium and minor actinide get deposited here. Then this is taken to the cathode processing, and the melting was done for removing uranium and also to take this plutonium and minor actinide. So this will be used for making the further the fuel for the future. So in this regard, we have set up a pyroprocess R&D facility with 10 kilogram uranium alloy, because we cannot use uranium plutonium alloy in public laboratory. So with the natural uranium alloy, we did a batch scale uranium electrorefining, and the entire the process flow has been successfully. You can see here the uranium pellet, the electrorefining unit. This is the deposition on the cathode. Then we scrap it and then melt it, and then this is what is the consolidated uranium ingot. So similarly, we have done for uranium zirconium as an alloy. Instead of just doing uranium zirconium alloy was also done. We have repeated the same thing and we have done it. Then with the permission of the department, the uranium zirconium slug that was used in the reactor
for radiation also has been successfully done. We have taken out, and the uranium has been successfully recovered from that. The ultimate thing was to do for uranium, plutonium, zirconium. So we have taken permission in a confined electrochemical cell in a radioactive environment. The unirradiated uranium, plutonium, zirconium metallic fuel, this was also electrolyzed by the electro-refining process. And you can see here the uranium, plutonium alloy rod into pieces. Then it is put into anode basket. And then this is the liquid cadmium cathode. And this is the electrode cell. You can see this is the uranium, plutonium, zirconium. This is the liquid cathode, reference electrode. This is put into the cell and electro-refining cell. Then finally, after one run, we have taken out the alloy after the one run. So we have now, have the laboratory scale process that is optimized. And similarly, for direct electrochemical reduction, instead of the uranium oxide, we can directly reduce and then produce uranium metal. And this is another similar to your electrowinning. So we have a 100-gram uranium oxide pellet plant, small plant, and this has been operated. And we are now further doing it with the other methods like the lithiated method, which I will show in the next slide. Before that, the molten salt after the reprocessing is left with a lot of impurities. So again, what we do, the salt is converted into oxide, and then oxide is converted into metal. So this is also used for processing of the the waste molten salt. And this is the electrolithiatic reduction, and this we have done as an advanced process, which is much more efficient than the previous one. And we have demonstrated and produced electrolyzed uranium metal. And all these technologies are never available in the textbook, and we have to evolve it on our own and bring it to the pilot plant scale level and wait for the reactor to operate and do with the electrochemical technologies. So in conclusion, I would like to tell you that why we are pursuing these electrochemical techniques, because it is very simple. The technique is very simple. You need your material as an anode or cathode, and you need a counter electrode, you need the medium, and you need power to be applied. And with room temperature, with less than 100 degree, we can do many processes. And this we can operate remotely. In a hot radioactive cell, what you do in a normal laboratory cell, we always handle it in a radioactive cell. So we have to use remotely operating manipulator and do this experiment. So electrochemical experiments that way are very, very convenient and easily operatable, and they are versatile. And that is where this is very important. So I have given you 4 different examples: electrochemical sensors and probes, industrial production of nuclear grade sodium, enriched boron carbide and boron, and electrocatalytic electrode materials for industrial scale electrochemical processes, and electro-refining and winding for metallic fuels. So the entire, the front end to the back end of the nuclear fuel cycle, from the fuel manufacturing to spent fuel, management, electrochemistry is used as a versatile tool. And I want to tell all the young people who are pursuing electrochemistry as your career, never get disappointed. Don't think that you just do kind of a subject that is not having great application. Please see, in a mission project like the atomic energy, electrochemistry has a very big role to play, and you should continue to be motivated and working on your electrochemistry project and on your research or on your academic activity. Thank you very much.
Thank you, sir, for the insightful lecture highlighting the importance of electrochemical techniques in various segments of nuclear reactor as a part to reach Viksit Bharat. Now I request Dr. K. Ramesha, Chair, and Dr. J. Madhyarasu, Co-Chair of the session, to honor Professor Kamakshi Mudali on the dais. Please, sir.
Now we have come to the end of the first memorial lecture. We will now take a short tea break for 15 minutes and assemble back by 11:50. Meanwhile, we request the dignitaries to inaugurate and open the exhibition of stalls. Also, we request the audience to witness the opening and join for a photo session in front of main building. We request the volunteers to assist the participants.